Okay, today it is everyone's favorite topic, projectiles. Hooray! I am not going to go over the basics of projectiles. If you need some review, hop over to the High School Physics channel. There's a couple of videos there on projectiles that gives you all the stuff from the ground up. We are just going to do a couple of examples of some more complicated problems than what you might have seen before. So to start out with, I am going to remind you of this wonderful equation here, the level range equation, stressing level. Please do not ever use this equation if you have a delta y that is not equal to 0. So if you are throwing something off a cliff, for instance, you cannot use this in that case because your delta y is not 0. If you're throwing something up at, I don't know what, some monkey in a tree, as we physicists like to talk about. Here's your monkey hanging in your tree, I don't know. Anyway, you cannot use it then. Only if it's thrown and land at the same height, delta y is equal to 0, can you use the level range equation. I will also point out that this initial velocity here is neither the x or y component, but it is the scalar initial velocity. So it is the total velocity regardless of direction. And then you don't forget the factor of 2 here as well. So there you go. This will give you the horizontal range if you have a level projectile. Okay, so first example, a rock is launched at 20 meters per second, level ground. Ooh, look at that fancy word. And it lands 25 meters away. So we will diagram this in case you can't picture it. Level ground, 25 meters from here to here. And we want to know the launch angle. Initial velocity was 20 meters per second. So you can set up this table to organize all your information as I go over in my high school physics videos. But since we saw this keyword here, level ground, this way is going to be longer and it's going to be more work. So we can jump to the level range equation, which looked like this, sine 2 theta all over g, 9.8. Okay, and we want to solve this guy for theta. We have everything else we need, so we can plug in 25 for delta x. Our initial velocity is 20, that is squared, sine 2 theta. And we just have a little bit of work to solve for theta. So if we multiply that and divide that, we're going to get sine 2 theta is 25 times 9.8 over 20 squared. And then we have to take the inverse sine or the arc sine of both sides times 9.8 over 20 squared. Throw that guy in your calculator. This is going to equal to 2 theta, so if we divide by 2, then that is going to give us theta. And this works out to be a nice 18.885, or I'll just round to 18.9 degrees. I'll make it squiggly signs there for the mathematicians who worry about stuff like that. So that is the initial angle here at which we were launched. Now, if you recall, there's actually 2 angles that will satisfy these conditions of having an initial velocity of 20 and landing 25 meters down range. And those angles are always at equal distances from 45 degrees. So if this is my 45 degree line here, here was one angle at 18 degrees. Okay, this is my 45 degree line. So another angle that is an equal distance, not 18 degrees above, because this wasn't 18 from 45, it was 18 from the horizontal. So these angles here, if they're equal, that will also give us the same range. So this guy would fall down here at 25, and that guy would go up higher, but also come down at 25. So if we find this angle here between this 18.8.9 and 45, so 45 minus 18.885, that is going to give you a 26.1 degree angle. So then if we have 45 plus that 26.1 degrees, that's going to give us this other angle here. Measured from the horizontal, this big fat angle here is going to be 71.1 degrees. And if you want to check it, you can plug this back in to our horizontal range equation. And let's go ahead and do that. And we should get 25 out. So we've got delta x equals same initial velocity. We didn't change that. We just changed our launch angle. So 20 squared sine of 2 times 71 point. And I'm rounding when I'm writing some of these, but when I type it in my calculator, I'm not. So please be careful to not do intermediate rounding. ... There's some more digits there. Plug that guy in, divide by 9.8, and lo and behold, you get exactly 25 meters. So in situations like this, there will always be two angles that satisfy these conditions. All right, let's look at one more problem. Kid throws a rock from a height of 2 meters through a window that is 6 meters above the ground. Building was 8 meters away. Initial angle is 35. What is the initial speed of the rock? So if we say here is the rock, and it was initially thrown from 2 meters off the ground, flies, what did I say, 10 meters this way? Yeah. And hits a window 6 meters up. So the rock did something like this, smash. Okay, we want to find the initial speed. We're given the angle. These angles, it didn't specify here, but the angles are always with respect to the horizontal. So that is 35 degrees, and we want to find initial velocity. Now you might think, oh, I can jump to the horizontal range equation and solve for that v in there. That would be bad news because delta y is not 0. So this is a case where you do need to break out equations for the vertical and horizontal parts. I'm not going to spell everything out. I'm just going to say over here we pretty much always use, not pretty much, we always use delta x equals vt because we have constant velocity. Over here we're almost always using delta y equals v naught t plus 1/2 at squared. And this initial velocity is the y component, so I guess you could specify that. This is the initial x component, or the final, since it's constant, it doesn't really matter. So this is what we're dealing with, and we can start plugging things in here. We know our displacement is 10, our horizontal displacement. Initial velocity is what we're trying to find. Now the x component is the total initial velocity, and the x component, if we think about dividing this up into a triangle, the horizontal component is going to be the cosine, so cosine of 35. So this whole thing here is my initial velocity in the x direction, so I still have to multiply that guy by a t. Put a line here. Okay, over here delta y, we go from 2 to 6, so our change in height is 4. Initial velocity in the y direction is, instead of v naught cosine, it's v naught sine of 35. This also has a t that we're multiplying by here, plus 1/2 at squared. Now, the displacement and the initial velocity are both up. Acceleration is down, so we have to be careful about our signs, so we need to make this negative. I'm going to go ahead and multiply 9.8 times 1/2 and just put 4.9, and then we've got t squared. I want to find v naught, but I don't know t. But as I'm sure you noticed, we have two unknowns, but we have two equations, so we can go ahead and solve those through whatever method you prefer. I am going to solve this guy for t and plug it in over here. So t equals 10 over v naught cosine of 35. And I'm going to plug that in over here for all my t's. So 4 equals v naught sine 35, and then for t I've got 10 over v naught cosine 35. Put a big happy bracket around that guy. Minus 4.9 times the same t, 10 over v naught cosine 35. And this whole guy is squared. Don't forget the squared. Now we can simplify some things. Nicely, these v naughts go away. We can combine that sine and that cosine, so that becomes 10 times tangent of 35. Over here, it's not quite so pretty, minus 4.9 times 100 divided by v naught squared cosine squared of 35. So this isn't too bad. We just have a bit of algebra left to extract that initial velocity there. So if I put this term over there and that over there, I'm going to end up with 100 times 4.9, so we might as well just make that 490 over v naught squared cosine squared 35 equals 10 tangent of 35 minus 4. And then if I multiply the v naught over there and divide this over blah blah blah, do algebra, you'll end up with this expression, taking the square root of 490 all over cosine squared 35 times the quantity 10 times tangent squared, not squared, sorry, tangent 35 minus 4. So that whole fat thing is in our denominator. Plug that puppy into your calculator. I'm doing this in degrees, so make sure your calculator is in degree mode if you're following along. And you get 15.6 if we round to one decimal place. Meters per second is how fast the rock was thrown to have struck the window at these distances and whatnot. All right, see you next time.